You can interpret everybody's stories and you can do it. You know, that day, it's fine, but I put in that cat. That's right. Yeah, so you need a lot of black lag. The surgery is exactly in 4 hours of that thing. And look at Broadway actually. You know, but yeah, I basically the scale that thing that I'm telling you that actually have a bunch of files on a long time ago. So does it necessitate policies? Yes. In the way we do the answer is that this is a big world. It's a big discussion that I've been having with my team for a long time. So that's the one is that you can what you say on context of verb. Yeah, so these are the ones that are what it means is that all the there are some theory quantitative statements. It's not always how the second one is. I don't have to do the paragraph. The why paragraph is if you want with the answer that I was working, I can construct four spaces. Is it one of them? What's the max? You know, yesterday you did that. I can construct four spaces. And you know, the four spaces are not the same as the four spaces that you learn from the original. The four spaces are algebra. But you can construct and you actually but in other cases, I do. For example, Fibonacci, it would be beautiful to those people. Right. So you want so versa. If you want to take that's important. I mean, let's give you that's even we actually that's for me as well. That's my problem. And yeah, but it is for you to be exactly right. So right, this is more so I want to yes, I want to so this is more no, sure. I mean, that's what that's okay. It's not sure. When I prove that in you can have that with that artist. Yeah, so I think we do it towards the end. Yeah, you know, I think that's good for you to be correct. When money was here, when money levels here, oh, left to unpleasant tasks. I had a call with the solicitors from the sellers of the house. Well, very unpleasant, very expensive calls. And they just wanted to be annoying about the repair for and there was like a bit of security and it's part of the experience. But when you go to this, if you like the house, eventually that doesn't. Yeah, I think it's World Cup. My question was, can you define equivalent of box spaces for this part? No, he doesn't know about it. He doesn't care. Absolutely, like he doesn't care. So I don't nothing like you're going to do that. Is there coffee tonight? Oh yeah. Sorry. So you know, for us, coffee. Yeah, it's coffee. But also, they don't ask you for cheap, but you know, all information about physical process are based on history. You know, in particular, really important is that we take qualification and look back at it something very exclusive, what it means. And you count, you know, the important counter, you said, oh, it was not for another fucking chip, another fucking chip. How do you translate this in nothing? No, this is a question. Okay, probably. So now, you know, say, you know, we put that about double bit that it gave. It's you know, where it's a good. Yeah.
I didn't get any slides.
Oh no, sorry.
At some point you can send them. I just want to make sure I didn't
sorry.
miss them.
No, I didn't know. It's fine.
No, I keep posting the videos, which is excellent.
So
Last part of the video this morning doesn't have slides, so I just have video of you being defined.
Huh? Oh,
It looks good. It looks good. No, it looks good.
But you know, for example,
Okay.
So suppose your generalized QSEc value. And I want to different part of that. You know, people talk about parameters, right?
Yes.
So the quantum theory set. But in that case, I can construct the particles, the focus parameters.
Yeah.
I can construct out of these arguments.
Yes.
So I can construct, you know, in the case you were talking about, you have to change these operators.
Yeah.
Okay, you have to change operators, and these operators should carry string. There's a string.
Today's 29.
When these operators carry the string, that is a particle.
Today's 29. Your first slide, 29.
Thank you.
So what I say is, in that case, you can do what you can convert into Fox space department. 1 theory particles. But in general, it's not obvious.
So let me see, just to start, just 1 second. Before I start saying anything, but I'll share the screen so that everybody can see the thing I'm showing. First things first, let's just select the right speakers. Sounds good. This is just a test. Fantastic. Okay, so it's recording, I believe, and I can share my whole screen this time. So there's this work on ignore the very highly mathematically annoying notations. It's going to be rephrased in a more physically friendly way, but just for the sake of giving you some references, the starting point for having particles in the way that my student Razin has been sort of, he's been building upon some previous work by myself and a collaborator from a few years ago about being able to write down ladder operators for bosons in scalar bosons, complex and real scalar bosons, in the terms of diagrams, diagrammatic rules. So figuring out some basic rewriting rules that can be used to perhaps do some interesting things with quantum fields. Obviously not complete in any way, because quantum fields are a huge space and there are way too many things to derive, but enough to sort of get started. And we took some notes in quantum field theory as our reference, and we said we're going to go very slowly and we're going to try to translate what we have so that we can show that you can get at least to Feynman diagrams for complex and real scalar bosons. So nucleon, anti-nucleon scattering, that sort of nucleon-meson interactions, that sort of stuff. Sorry? This is on the archive, yes. But we are currently, before we send it to a journal, we are rewriting it so that we hide away the potentially scary bits. Oh, pretty much all of it is scary. Sorry, yes, I will put the reference, but so the page, that is effectively, yeah, Yeah, there's an abstract. There's an actual abstract, but that acts as the abstract. That figure is, and then we'll go into the details, I guess, if you're interested. And
Tested the audio.
Yeah, the audio is tested. It's
the
people. Yeah, I mean, I can double check that they can hear. But Amir, can you?
Yes, all good. Perfect. Thank you.
Thank you so much. Yes. So this particular figure is an example of diagrammatic rewriting that we included sums explicitly because I thought that compressing sums into, you can do it with just diagrams, but it is a bit clearer for the purpose of connecting with previous work to just have sums of amplitudes effectively. And you can show that if you take two Feynman diagrams, you turn them into ZXW circuits, and then you compose them sequentially, then the rewriting rules for the commutation between the creation and annihilation operators, they automatically, when you try to put them into normal form again, so you try to push all the deletions to the left and all the creations to the right, automatically they give you all the possible compositions of the diagrams into connected or non-connected. So you have the 4 particles in, 4 particles, you have 4 particles in total, and you can have sort of 4 in, 4 out, or 3 in, 3 out with some virtual in the middle, and you get all the possible compositions this way. So you're saying there is, by diagrammatic reasoning, you get this compositional notion of diagrams where you take 2 terms and putting them in sequence automatically gives you all the superpositions of all the possible ways in which these particles interact in sequence. They could be separate, they could be connected with a virtual leg in the middle, depending, you get all of them. So from the left where you have 4 in, 4 out, to all the way to the right where you get 2 in, 2 virtual, 2 out. So that's automatic. That's just a consequence of diagram rewriting. But the basic idea, ignoring for a little this, and I won't really, there's no need to really go into the details too much, but it's when the other day you said you don't really take the reals, you take some sufficiently fine grid, sufficiently large grid, and maybe it wraps around, but as long as you stay in the part that's nice, everything works out. That is the starting point of all of this work. It's to saying you take the real numbers and you approximate them by a cyclic group that is so large and rescaled by an infinite, so finely meshed, that actually every standard real value is covered by one of these points, and you never get to see the wrapping around because that's for way past infinity. So your reals are actually tiny, tiny fraction of the whole circle. But the advantage of doing this is that from the point of view of non-standard analysis, this particular group is finite. It's a hyperfinite group. So it's finite from the point of view of non-standard analysis, but when you try to interpret it in the standard way, it is not just infinite, it is more than continuous. It has so many points that it covers all the reals and more. So one of the things that we really want to hide, because there is no reason we want to publish it in a journal, we want to submit it to a journal that is okay with some of this foundational quantum stuff, but not necessarily going to be too happy with all of the non-standard jargon. So there is all of these techniques, this idea of finally meshing the intervals, of summing over infinitely many points and then dividing by infinity. All of these are already in the original book about non-standard analysis, and they are the non-standard version of integrals. So what we'll do is have an appendix that explains that integrals are implemented like these sums, and we'll replace them with more traditional notation in the paper. So we're going to do integration, and we're going to use delta functions. We're going to use the sort of standard notation, and then at the last part of the paper, we're going to say, actually, when you read an integral, really you should think it's a sum. But that's so cosmetically, this is a bit rough, and it will have to change. But the basic principle remains, and I think the important part is that instead of considering the creation and annihilation operators, so the ladder operators, you make a controlled version of the ladder operators. In fact, you make a quantized version of the control ladder operators, so coherently controlled. And you say, I have my Hilbert space where the field lives, in and out. I have my ladder operator, which is parameterized by, let's say, momentum. So I'll take them in momentum space. And then on the side, I put one additional quantum system, which is wave functions over momentum space. So I quantize the control parameter. And I do so for, it's enough to do it for one operator. The other one is obtained by just adjoints. And the nice thing about working this way controlled is that you can plug in momentum eigenstates. So momentum states in the momentum basis, and you get the traditional ladder operators in the momentum basis, or you can plug in position eigenstates. So the Z basis, the green spider basis, and you automatically get the positive and negative frequency parts of the field operator. And so you can write, you can take these sort of one building block is enough, plus its adjoint, you change basis, and depending on the basis you use, you can sort of construct all of the various pieces. You can integrate time evolution. So you add sort of controlled one of these algebras that encodes the time evolution operator, and you shift into the Heisenberg picture, and you get these are the building blocks for the Heisenberg picture. So you get these operators that have both the space and the time, and that one is the green basis, one is the red basis. So it's kind of, it is the ZX calculus for a cyclic group, but this cyclic group is big. It's a hyperfinite cyclic group, but the rules are the same. So the reasoning works the same, except things that would be sums are actually integrals. The eigenstates are secretly delta functions or plane waves. They are unnormalizable, but we have infinities, algebraic infinities. So to us, they are normalizable. We don't have to care about any of this. There's no limits that need to be taken here. And then we have these basic sort of building blocks. And from those, we can construct Feynman diagrams. So we introduce Feynman propagators, which are just a way of producing scalars given position, two four positions, 2 4 vectors. You get a phase. And from that, we can effectively take the expression of a term of the S matrix in terms of its operators. We expand it like you do in Wick's theorem. You get something like this, which is linear, because the point of Wick's theorem is really you're applying the operators linearly to the space. You're deleting and constructing, and even in normal form, it's still a linear sequence. It's just one, then one. So first delete, then delete, and construct, but it's on the same space, and that's kind of not nice. That's not what we want, because it doesn't give you the compositional degree of freedom of parallel composition. So it doesn't capture diagrammatically the idea that actually some of these deletion operators commute. So you have particles coming in and particles going out, and they're independent. So that's missing from this description. It's linearized, but you can just do rewriting. For example, you can observe that all of these, this sum over x1s and x2s is just conservation of momentum. It's your standard sort of integrals. And you can replace them with spiders. So you insert these maps, which I'll discuss shortly. I'll tell you why they're there. You sort of push them forward, and they open up the deletion, the annihilation and creation operators into 2 branches. You can sort of slide them, and then you fuse everything, pull it up, and what happens is something like this. So you have, ignore for a second the split and merge at the left and at the right. That addresses the question, how do you get the tensor product in, which is a fundamental question at this point. And we had to work quite a while to figure out what a good solution would be. But on the left, you have 2 copies. You have 2 particles. So 2 of these Fock spaces coming in. You annihilate a nucleon each. And then what you're left is the space after the annihilation effectively, but you also have wires that carry, if you will, the measured momentum, the momentum for that particle. Each of these annihilation operators carries a momentum, and you're summing, integrating over the momenta, and the integration, that the part that says that the momenta have to sum to 0 is this green spider, because a green spider is a sum for the momentum basis. And if you have a green spider with just legs, it says the sum of the momenta coming in has to be equal to the sum of the momenta going out, and it's a superposition over all of them. All the possible combination of the momenta going out that have sum equal to the momenta coming in. And that's just a conservation of momentum part. And in the middle, you have the Feynman propagator for whatever. What did we have in the middle? I don't remember. We had some meson, I think. Yeah, there was a meson in the middle from sort of scalar Yukawa theory. And that is the diagrammatic equivalent of the Feynman diagram. It contains the same exact information. And you can play the same game, and you can do calculations with it. You can get scalars out of it. So you can reconstruct all the calculations from quantum field theory from these Feynman diagrams, the amplitude calculations, you can do just diagrammatically, rewriting things and simplifying them. The hard part, conceptually, in my opinion, is this idea that actually you are starting with a single giant Hilbert space. This tensor product of harmonic oscillators is kind of it is a tensor product, but you can't really split particles as if it were a tensor product because some of them might have the same momentum. And so the point is you might have two mesons that have the same momentum, and it's not a tensor product, it's the ladder, it's a direct sum of state. So you have to find a way of splitting this giant space into two parts in such a way that each particle goes on one side or on the other side, and you take all possible combinations of this. And this is what the split maps do. And in fact, it recently turned out that these are the W spider from the ZXW calculus, which is work that my co-author, well, the student who did this, then went on to do a PhD, and recently he's been working on the ZXW calculus, which has this W spider, and he realized that, well, it's the same. And the idea is you take each particle and you send it either on the left or on the right, never both. So you always conserve particle numbers. But because you have all the possible combinations of particles, you get the ability to slide annihilation operations in any way you want. So you can say, I annihilate a particle before opening it up, or I annihilate it in one of the branches, and that's the same. It gives the same exact result. So you can use these split and merge maps, they're just the adjoints, to take your individual Fock space and open it up in many copies in such a way that you can really slide, you can do the deletions in any order you want. Of course, you cannot commute them past creation operations. That's not what this does. But you can sort of open them up and do them in any order, and you're going to get the correct result. So this gives you the opportunity to take linear Feynman diagrams, going back to the picture. You take a Feynman, effectively a term of the S matrix, written linearly as application of the deletion and creation operators on the same space. And then you introduce these split and merge maps, which are, the split map is an isometry, so you can just plug it in. And then you sort of scroll all of the deletion operators forward, all of the creation operators backwards, and you get an equivalent representation of the same diagram that now has the parallel component visible. You use the spiders to impose conservation of momentum. That's just the sums. The sums are going to be just the spiders. It's the definition of one of these position-based spiders. And you get a diagram out of it. And that's pretty much you can do the same game with any diagram for scalar bosons, and it always works. And my student has recently been working on fermions. So he thinks that he has a solution that would work, for example, for electrons. And he says that it should be not too hard to get the same trick to work for vector bosons, excluding issues with gauge and such. So issues with gauge may have to be worked out separately. That's me remembering my quantum field theory training, saying I wouldn't be quite so confident that the same trick will immediately transfer to vector bosons, but he is pretty confident that as a starting point, he will at least be able to write the Fock space. Yes?
Why wouldn't you have a problem with fermion? Because I would imagine that the space of fermion is easier to deal with. It's not ladder.
It's the space for fermion is easier.
Yeah.
So with fermions, I have no concern.
Oh, I see.
It's just that these W spiders were originally worked out for qubits, then for qubits, and the ones for qubits work well for scalar bosons, and they coincide with what we already developed independently. But he says actually the same exact trick works for fermions, and he's done the board and done the calculations, and I am confident that that works. It's just not being written yet. Or anything you want, you can just interrupt me.
With fermion, you've got a sign. So when he's having all these sums, that less sign, in fermion, that is not going to be. Okay, so on one hand, you have the exclusion Pauli principle, that is like a qubit, because you can't have two fermions in the same mode. But on the other, that is not the case with both, but on the other, you have the exchange. And the exchange is going to add a sign to everything. You have to keep track of the sign.
Yeah.
Okay, that's it. Now, the thing that I wonder is, I mean, here you put Planck Gordon. Okay, that is the thing that you put, and Planck Gordon is special.
Yes.
Okay, so because Planck Gordon is a harmonic oscillator for quantum fields.
It is, yes.
Quantum fields.
Yeah.
Okay? There could be, some complication, for example. I mean, as long as the interactions are local, and you are doing also one dimension, that's the other thing that you have to do. This is doing in one dimension space, 2 dimensions, 1 plus 1. So it's one spatial.
Oh, no. This is arbitrarily many space dimensions.
So the x1 is a vector?
It's a 4 vector, yes.
Okay, but if it's a 4 vector, x1, with fermions, you are going to have serious problems. I mean, it's going to be much harder, I guarantee you. This is the same. In 1D, it's almost the same. Modulo counting the thing. When you are in 2D, the problem is that the fermions carry, because of Jordan big, they carry string. So it's not so trivial to look at the string. Because of the as long as you have kinetic energy, it's very hard. You cannot eliminate it. I have a bet with Frankfurt thread. He claims that you can eliminate the string. It's impossible to eliminate the string in 2 dimensions. Or 3. I mean, I'm just saying 2 plus 1 because
fascinating.
It's simpler. High dimension. With fermions in high dimensions, you're going to have problems.
But why would the space be
matters because in 2 dimensions it's the same problem. Why in 2 dimensions if you have arbitrary particles you have the gradient and you don't have just the permutation group. So in 2 dimensions when you have fermions, 1 dimension there is only one way to fermion because you cannot pass through a fermion. Then it's very easy. It's some sort of trivial exchange. But in 2 dimensions, there are many different ways of passing a fermion. Okay, and these different ways are characterized by a string.
I get that. Okay, so maybe this is where I was confused, and perhaps this is a point where nomenclature starts mattering. The diagrams, the fact that I drew them in the plane in parallel, did not in any way imply that there was a planar structure to the interaction. So this interaction drawn in the plane is not actually, and here is perhaps an important point to make. This is not actually saying these 2 particles are at 2 points of a line. So we're not working in what you'd call, I don't know, a 2 category, for example. In a 2 category, you'd actually interpret the diagram, the wires as the world lines of particles so anions, let's say in 1 plus 1, and the boxes as the interactions between the particles. And there's color that you have to keep on left and right that gives you, I don't know, the local charge left and right of the anion. So there you have an issue because, of course, I don't even know what a fermion does in 1, given that they would have to pass each other and there's no way for them to pass each other. So
they cannot pass each other, but there is
interactions.
No, but still the interaction is playing a role because, the sign is a super selection rule.
Of course, yes. So you're working. Yeah.
So what happens is that it will depend on the nature of the interaction. So if the interaction is local, you have some local interaction, like a cover interaction, something like that. In that case, it's a kind of C in 1D. Yeah. If the interaction is 1 over R, 1D or logarithmic or whatever that you put,
then it's complicated. Of course. So we are not working in that formula. So we're not doing what you'd call perhaps a topological quantum. I'm going to say topological quantum field theory. I don't necessarily mean only topological quantum field theory, but there's all of these approaches to calculations that rely on identifying wires with world lines and boxes with purely local interactions. And there is no local interactions in these diagrams. So some people use that in 2 plus 1. So they use 3 categories or monodal 3 categories. Monodal 2 categories or symmetric monodal 2 categories to try and talk about anions in 2D. So both fermions, but also more exotic anions with complicated rules. And that is one use of diagrams. And then there is the other use of diagrams where one of the two directions is a tensor product, but there is no spatial component to the tensor product. So here, this is what we use. This is more of the quantum information use of diagrams. The tensor product is just an abstract. It's a way of keeping track of the fact that those two operations commute. So they are now on two wires because I can apply them in either order, and I put them on two wires because I can then use the topology of the plane plus plus, so the technically 4D string diagrams, to do calculations of the information behind the particles, but the wires do not represent particles in space-time. So I do not have any braiding problem. The problem that I get to swap the fermions is in the split map. So it turns out that this split map for fermions keeps track of the order, and there's a minus sign associated with where you send your operator, so that if you swap the legs, you get a minus sign in. So it is the difference between fermions and bosons, or in general between anyons and bosons, is actually in the way that you informationally open up the space, because you have to remember the order of because now the order of these operators matters up to a phase, of course, but still matters. But once you've opened it up, these two wires simply represent two copies of the Fock space, and there's no spatial degree of freedom there. The spatial degree of freedom is purely carried by the momenta of the particle or their position. And the wires braiding are not braidings in space. So yeah, the pictures are suggestive because of course Feynman diagrams are suggestive, right? You draw Feynman diagrams and kind of imagine that you truly have two particles coming in and some meson exchange and particles go out. But of course, if you have fermions, you have to be careful. You know that if you sort of swap the legs, then you introduce a minus sign, so that you're trained to introduce those two legs. The swapping of the legs is not actually the swapping of the wires. It's the swapping of the outputs of the split map. So it's having the split map or the split map followed by a swap. And that's the point where you get the -1. The swap itself is a swap in the information theoretic sense. It just takes not two particles. It takes two quantum states in a tensor product and swaps them. And that doesn't carry any physical meaning. It's just information. The physical meaning is in the split map. When you open up the tensor product, if you open up like this, or if you open up like this, that's the minus sign. That's where the minus sign comes. So you can sort of hide the phase that comes from the inversion of two particles in the split map. What you can't do is keep track of more interesting topological information. So you cannot, for example, take two onions and ask, what does it mean to do this? Or what does it mean to do like two things? That is not graphically captured in this formalism. If you want to capture it, you'd have to reconstruct it from the terms of a Feynman diagram, but it wouldn't be a diagrammatic thing for us. While there are people who work in sort of these diagrammatic approaches to higher topological quantum field theories, they would be instead interested in saying, we have a category where there is an interesting braiding, and this braiding in space with color for charge keeps track of the phase accrued by topological onions. That is a hard field, and I'm not completely out of my depth.
Let me reformulate my concern in your language. So if you have fermions for those, that implies that you exchange two particles, you get a sign or not, depending on the character
of course.
The particle. If you think in terms of an algebra, okay, of the canonical commutation relation or canonical anti-commutation relation, etc., etc., these commutations do not depend on the rest. So you take two modes, or you take two indices of these fermions, that's what you're telling me, and these two indices you exchange and do not depend on the other indices. Okay? Now, you have anyons, which are not bosons of fermions, but they carry some representation of the Gray group, either because they have abelian and they carry phase,
or
they are
non-abelian,
non-abelian and they carry a matrix.
of course.
In these two cases, what happens is that the exchange of two particles depend on all the other particles.
Of course.
And that is a mess. Okay, so that is a real mess.
I mean, there's this, and
because you have to pre-establish an order. So you have to say, well, I have 100 anyons, I will label this canyon here, this mode is 1, this is 2, this is 3,
Correct.
this is 4, this is 5. And then it's a mess to, just follow or keep track of anything because, just taking 2 and 3 is not the same as 1 and 3. Because
of course
1 became before 2, and then, there is a whole thing that it's really a mess.
So this is not something that we plan on tackling with the extension of this work that, by the way, is not out. So there's it's entirely possible that now that you've mentioned this, I'll go back and say, Razin, sit down and check. And you will be like, oops.
Simplest check you can ask. It's a simple check that is going to be, a simple extension that is going to be very useful if you are dealing really in 2 elements. 2 plus 1. That is the Carpel boson. Because the Carpel boson is not the canonical boson. Now, you don't have the usual Fock space as in the other 2 cases. So every time you take 2 bosons, they are like a boson. But you cannot put 2 bosons in the same place. I
see.
Okay. That is let's say, the simplest extension of this idea that is highly non-trivial.
So it's like it has the exclusion principle like fermions, but it doesn't have the minus sign that comes from the. Correct. Interesting. I did not even know that had a name. Okay, that's very good. Hardcore as in.
You cannot put 2.
You get it now. Okay. Actually, yeah, we actually that is probably worth having in as an example. We can start from that because that's simpler and that should be okay. Cool. But
it's kind of clear. I will tell you why. Because in condensed matter for a long time, we know these things for a long time. It's not new. Even I think that the things come from maybe the 50s or 60s.
Mm-hmm.
But there is no weak theorem. There is weak theorem.
Well, then there is no hope for us to incorporate them.
Can do something.
You're giving me a hard time. Like you're coming here and telling me. No, because there is weak theorem for fermions.
For fermions and for bosons, there is.
And for vector bosons.
Yeah.
Correct. That's.
If you go to Carter bosons, there is no weak theorem.
Well, then I should probably mention that the entire trick that this is based on. That I'm not going to, in any way, I'm not going to touch that. We rely on Wick's theorem. The entire trick relies on Wick's theorem.
No, that's okay.
So we are. So it's going to be very hard to incorporate that case because Wick's theorem is at the basis of the trick. There you go.
I mean, the idea is this: many physical systems are not really bosonic, but they are almost bosonic. Helium-4. Helium-4 is the simplest example.
Yeah. You swap, that's fine, but you can't put 2.
But you cannot put it together because it's an atom. So if you have a gas of helium-4 atom, the description is not fermions, the description is not bosons. It's Carter boson.
I always wondered what it meant to have like hadrons that behave like bosons, and I always wondered under which circumstances it made sense for them to pancake. And it doesn't, because you can't put 2 helium atoms on top of each other.
No, I know, and you cannot put in optical lattice when they say they have bosons. Sometimes they say, oh, we have 3-value recombinations, everything. These are Carter bosons. These are bosons precisely for that reason. They go away. You cannot put 3 atoms, 4 atoms in the same position.
Yeah.
I have 2 questions. So the first one is, so you are assuming relativity. Right?
Yeah, this is.
Would it matter if you do like a Schrodinger field instead of a so non-relativistic boson?
Yeah, it would be the same, but the definition of the propagator would be different. So this term is there's some normalization factors that are relativistic normalization.
Will that mess around your decomposition of 5 plus 5 minus?
No, it just would change the way that they expand. It would change them, but the rules that govern the diagrammatic rules, that's the point of the diagrammatic approach. You try to encapsulate all the complexity into the boxes, and then you try to only use rules that tell you how the boxes interact. So as long as you get something like a commutation or an anti-commutation relation, you can still do the same tricks. They will go through. You're just going to gain some different signs, different phases. But what the relativistic factors are there for sake of completeness. But if you remove them, you just get different expressions, but they behave the same. So you can still do calculations. The results are going to be different, of course. But
I think that your question is to test the Dirac.
Exactly. Yeah.
the Dirac field. The Dirac field.
The Dirac field.
The discretized Dirac field. That doesn't even require this stuff. There is like quantum cellular automata approaches to the Dirac field. We have. So, hang on. Where is it? Tutorial, evolution of quantum fields. Yeah. Hang on there. I'm gonna get there. So, something like that. So you imagine that's a generalized version of the. I guess I don't think I have a picture without the discarding maps, but I guess this is a good time as good a time as any to show this. So imagine that you have a bunch of sites in space-time, and they're connected in a lattice, and at each point you carry 2 copies of a qubit, or 2 copies of any Hilbert space. So you don't really need to have qubits. The idea is that 1 copy carries the right moving mode and 1 copy carries the left moving mode. So you have 2 modes, each of them has their own degrees of freedom, can be qubit degrees of freedom, but can be more than that. And one of them moves left at some speed, and one of them moves right at some speed. And the way that you can discretize this is by saying you take a lattice, a diamond lattice, so a lattice like this, and you have points, and you have arrows that connect each point to the points in the next stage of the lattice, so the next time step, one at the left, one at the right. And the way that the wiring goes, the way that the information propagates is you have the mode that goes leftwards, the mode that goes rightwards, they interact, and then one moves to the left and one moves to the right. And then they interact with these local interactions that discretize the evolution at one time step. And this evolution is localized to the 2 sites next to each other. And you then move them, you evolve and then split them and move them to the next, to the right and next to the left. And you continue doing this. And you study the evolution of these systems. And the evolution of these systems is a quantum cellular automaton. So it's a discretized time, space-time in some way. You put a lattice in Minkowski, and you put some lattice, so as in a graph, actually a directed graph, which points consistently in the correct direction with time. And then you make local interactions on this lattice, and you sort of compose it in parallel and in sequence, and you study how the evolution works. And for this particular automaton, and here I'm gonna have to pick up the original overview, which is by Pablo Righi. Hopefully this is free, otherwise I'll go to the archive. It's okay, I mean, we can. And I think here somewhere there's a reconstructed simulation, or maybe it's in the previous literature by the Pavia people, somewhere. They show you that effectively you can, if you take the limit of this, you can of course compute the, maybe this picture is slightly clearer than the one I had. So you can track effectively the state of the automaton over time, and you can prove by computing some large scale quantities that if you take a limit of fine mesh, this in the limit reconstructs the direct QCA in 1+1. And there are categorical approaches to this that are not necessarily diagrammatic, but some of them are partly diagrammatic. So you can, for example, say, I want to have some way of describing what it means if I set the initial state on some slice and I want to compute the state on some other slice, where a slice is now it's sort of a discretized version of the space of states. It's a tensor product of the particles on the points, the discretized points that fall into the slice. And you ask, okay, what does the process look like diagrammatically? And the answer is, you take the cellular automaton and then you put these discarding maps that we talked about this morning, so that's partial traces, and you follow them down and you get that some parts of the system are, the original slice are already discarded because they're not in the passed cone for the final slice. And then you have the automaton that sort of proceeds, but some of these wires go out of the passed cone and you don't need them, so you can trace them. And this gives you the linear map. So this is the CPTP map associated to the time evolution from one slice to a slice in its future. So this is, and you can package it nicely and make a category of slices, and you can do all sorts of reasoning about this. So it's a kind of bookkeeping operation for this quantum, for these field theories, discretized field theories. That is not purely diagrammatic, but it is categorical. So it's uses shift theory to do some of this stuff. So there's work in various directions.
There is a quantity in the question. Is there any quantum version, quantum cellular automata version of the Wolfram's rule?
There would be, yes. Yeah. I'm pretty sure that they have them in.
Yeah, I'll come up with it.
Well, it's going to be one of these QCAs, but if I remember correctly, Wolfram had they had some posts about using these rules for quantum systems. They would be considered quantum cellular automata.
Yeah, but I mean, you know, the beauty about these rules is that these rules produces very complex, type of spectrum from very simple rules. You classify all this in one dimension.
Yes.
Now the question is, if you make it quantum, I don't know how, I didn't think of that, but now you're talking about a quantum cellular automata. If you make this rule quantum, that was at the complexity of the patterns or the complexity of what you get changes or does not change. I
don't know if Wolfram has classified this. It wouldn't surprise me if he.
Wolfram is not quantum.
Oh no, he's into They've introduced a lot of like quantum tensor network stuff to Wolfram Alpha. He's like started doing some. It's a fairly recent thing. But, he is. So it might be that that they already started looking at it. I never looked. I will. It might be that they already started doing something like that. I recently only, but you get something like this, right? You get something like these. So a bit of the, if you study sort of if you do it for qubits and you look at the pattern generated by the probability distribution of the local state for each qubit in this lattice, that does give you a certain picture that is maybe if you decohere it, you get some classical cellular automaton, but it's not a classical cellular automaton because underneath it, there is a quantum evolution. You're like looking at the classical picture of a quantum cellular automaton, which is different because you don't have enough information classically to do the evolution. So you're doing it, the evolution, you have to take the entire state into account because otherwise you don't get interference. So that's why these people study them as approximations of space-time. I am into indefinite causal order. That's part of my current research interest. So people do it to try and imagine what it would mean to have a quantum space-time and what it would mean to.
No, but when you measure at the very end that these, incoheres or does something, I think that there are certain factors that are classical that are stable.
Yes.
From the point of view of measure, I could imagine.
Yeah, that's.
There are certain rules that when you quantize that now you project are unstable.
Yeah.
In some way are not going to be preserved. Something like that.
Yeah, something like that. I have no idea whether this has been looked at, but certainly worth. Yeah, very. Yeah, absolutely.
Hey, Stefano, can I ask you, because you said today in the morning, you are continuing.
No, I think he had a question.
Oh, I just want to go back to the quantum field theory case.
Yeah.
So what would be the classical field of that? Like, is it still like a two wires rule that we introduced?
No, this is purely a single wire thing. You'd make it it is a 2-wire thing when you do in this particular paper, it's just unitaries.
I mean, your paper.
In this paper, it's doubled. But sorry, I should, I guess I gave you a simple perspective on everything and I should have been a bit more nuanced. So let me give you that and then Gerardo, I'll come to your question. So when you look at these theories, these diagrammatic reasoning theories, in the ZX calculus, you want to remember that you had doubled wires and that secretly there's some rule that allows you to, and allows you to just get the ZX calculus in again and to do some more reasoning. But if you are like me and you work mostly with probabilistic, wow, something happened to one of the screens. You did something this morning that worked, so I'm going to try that.
You know what it was.
Yeah, I mean, no, see. It's going to happen. Or did I?
Good, here we go.
Excellent, so it worked. So if you come from the ZX calculus, you want to have thick wires or double wires. Let me make them extra thick for extra clarity. So you have a sort of something like this, where you say I have a unitary, which has a quantum part and a classical part. And so I have, let's say, here C to the D, here, I don't know, C to the A, C to the B, and here I have a classical system, so R plus to the C and R plus to the D. So you have an instrument, quantum instrument, classical input, classical output, quantum input, quantum output. And that's okay, but sometimes you don't want to spend all of your day writing doubled wires or thick wires because you are lazy, like me, or maybe you're not, maybe you're very dedicated, but after a while it becomes a bit heavy on the hand. And so you start doing something a bit lighter and you instead write your boxes with single wires, with the understanding that these single wires are quantum and have a discarding map or are systems in a classical theory of some kind. And then if you want to really, and then maybe you write it like this, maybe you have some notation that explicitly distinguishes the classical systems from the quantum systems, something like that, but you pick a slightly simpler notation. As long as you have somewhere a discarding map written down, it's sort of, it is implicit in many of these works that if you see a discarding map, then you are working with a double system, because it doesn't make sense to have discarding map for a pure quantum system. There's no discarding in pure quantum theory. So if you see discarding maps flying around, as is the case in this work, then it is implicit that you're working in some probabilistic theory with discarding. And there are many, by the way, there are interesting probabilistic theories that don't look like quantum. So maybe that's something that I can then talk about today. In fact, that was part of my original plan. But first, Gerardo, you had a question.
Started asking at the very end when you were talking about learning non-locality.
Yeah. Yes. So shall I go back to that?
Yes. I mean, what I wanted to understand. The way you explain, I did. So in the case of Merlin's argument, I mean, he has to construct a weakness. And he has to construct some quantity that he knows that he puts plus, minus, minus, minus in your 0, 1, 1, 1, 1 cases, you know, plus and minus, minus, minus.
Mm-hmm.
When you add those things, you get 4. Okay, because I mean that is, you know, it's done in a way such that, you know, you get the number 4.
Mm-hmm.
I missed that part. So I missed the part. Where is the 4? I mean, how is that the 4 counts? I mean, what is the argument? I
hadn't yet gotten to that because I didn't have the time to discuss it, but that was my plan for the afternoon. So I will, okay. I'll use Mermin as my example for what this study of non-locality using diagrammatic processes is. So just study of non-locality technically is
non-locality or contextuality?
Well, they are the same. They're just different. I knew that you would object, and I am ready. No, I am ready, and I will fight on. This is a hill that I will choose to fight on. They are different, of course. Non-locality is physically meaningful because it derives, in a sense, non-locality is a special case of contextuality, which derives the contextuality from the assumption that there is no signaling between some of the parties. And then contextuality more generally is the observation that you are picking some set of measurement choices that have to be compatible some of them may not be compatible, but the fact that you don't pick all of them to automatically be compatible exposes you to the question, can I give a description where all of them can be defined at once? And that is, in that sense, contextuality subsumes non-locality. But it is also true, and I'll take the point, that people tend to say contextuality to mean that kind of contextuality that is not just non-locality. So people sometimes talk about contextuality arguments and they tell you they're not the same as non-locality arguments. By contextuality, I mean that I put some information about the fact that I know these measurements commute. And to me and Nicola, in our conversations and our philosophical view of this world, that is not theory independent, nor it is device independent. You have no way of knowing that anything commutes unless you look into the box. And because we're interested in device independent arguments, which are stronger, we treat both the same. And we just say it's an assumption you make in the world. One of it derives from the observation that you're very far away and hope that there is no magical signaling box. And the other one comes from your knowledge that the thing inside commutes because you know something about the device. But we will step back and say we will be agnostic and we'll have a unified way of saying all of these scenarios are a special case of something mathematical a bit bigger.
Yeah,
I completely, yeah, I know you didn't. I know you didn't.
I'm saying that basically many of the problems that they are, arguing that they are measuring Bell's inequalities, in reality, the systems are here. There is no.
Exactly. So there is no non-locality there.
Exactly.
That is absolutely the case, and it makes it, honestly, maybe after we stop recording, I'm going to make some statements about that. So they're not preserved for posterity and they remain here ephemeral. But I agree, 100%. I fully agree. I was just being facetious in my exposition. It is contextuality, non-locality. Contextuality to me is a more general statement, but of course, it's also true that people say contextuality to mean specific things. And at the same time, non-locality requires the physical assumption that the stuff is far, that there is no way for signal to travel from one to the other. If there is, then it's not non-locality. And there, by the way, you can prove that if you don't have non-locality and you don't impose contextuality, then you always have a classical explanation. There's like these theorems that say that if it's totally ordered, then it doesn't really matter what you do, it's still going to be classically explainable. So there's no hope to get anything non-local. But going back to Mermin, imagine that you have a box. Okay, some box, big box. And this box has 3 classical inputs and 3 classical outputs. They are binary, 0, 1, for simplicity. Then whatever this box is, what I know for certain by the rules of these, by the interpretation of these diagrams, is that this is a matrix, for sure. And it is a matrix of, positive real numbers. Wow, I'm not going to be able to do the belongs to. So it is a matrix, and it's an 8 by 8 matrix. In fact, it goes from 3 bits in to 3 bits out, but it's an 8 by 8 matrix. And if I further require that this box satisfies the following equation, so that I can discard the outputs, all of them, and I obtain the discarding map on the inputs. So this normalization equation implies that the matrix is stochastic. Or, for those who don't want to use big words, it is a conditional probability distribution, which I prefer. I think it is more expressive. And so really what happens is that you can represent this conditional probability distribution by a matrix or by a table or something like that. And yeah, thank you. Let me just delete things. What you get is something like a table, an 8x8 matrix, but I will organize it as a table. And so you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And here you have, so this is going to be the input. This is going to be the output. And I'm going to take 0, 0, 0, 0, 0, 1, 0, 1, 0, again, 0, 1, 1, 1, 0, 0. I have a point, I promise. And now each of these lines is going to be a probability distribution. So for example, I'm going to put some numbers in, and I'm going to say, let's say that this is 1 over 4, 1 over 4, 1 over 4, 1 over 4, and 0, 0, 0, 0. And then this is going to be 0, 1 over 4, 1 over 4, 0, 1 over 4, 0, 0, 1 over 4. And I promise I'm not making this up. Something like this. And perhaps some of these lines, some of these parts of the experiment that do exist, they give a probability distribution, but perhaps I don't care about them. May I restrict myself? I run the experiment with my 2 pals. We go far away, we do this like 1,000 times, and then we only look at some of the rows. And some of the rows we are like, that's not relevant. That doesn't give us information that we care about. So we just say, okay, those rows we don't really need to know. So we can select a subset of the inputs. We can restrict, condition, or constrain our inputs to fall in some subset. What subset? Whatever comes in handy. It's not really that relevant. And here, the model that I wrote on the right is actually the model for the experiment that I described this morning. So it is the model for Mermin. I wrote a circuit, but the circuit, technically speaking, had some parameters that I sort of left free, and I said, this can be 0 or pi over 2. That is a controlled operation. That is someone having a bit of input and deciding whether to do a 0 rotation or a pi over 2 rotation, depending on their input. So really, that is in itself, that's something that the various parties did, and I kind of hid it in the woodwork. So the model that I had was something like this, where the 3 parties each had a controlled rotation that they did. So in fact, I could perhaps write it as a control rotation on its own. So yeah, I'll write it like that. So this is a control x rotation by pi over 2. So it's Rx pi over 2, but with a control. And the control is these input wires. There's a 0 or 1 that determines whether the rotation is done or not. And I restrict myself to the case where exactly 2 of them or none of them are done. I don't consider the other cases. So I restricted myself to either no one or exactly 2 parties rotated by pi over 2. That's my condition on the inputs. And after the rotation, each party does a measurement, and that measurement yields a binary outcome. And that is the full box, if you will. So this is also 0, 1. So from the point of view of non-locality, I really just think of these as sort of diagrams that have some classical inputs, some classical outputs. And if you don't have anything else, because you might think, oh, measurements are really not like that. So I had these measurements where I had a particle that comes in and a classical wire that goes out. And that may appeal to some, but others might say, where did the qubit go? Are you hiding it somewhere? Is the qubit safe? Technically, this measure, sometimes it is sensible to say that measurements are demolition measurements, so the qubit doesn't exist anymore. You have a photon on the line, you absorb the photon, end of the story. The photon ain't there anymore. Done. Sometimes, like in the case of superconducting qubits, you want non-demolition measurements. So you want to say the qubit is still there. It just changed. I did not throw away that piece of silicon. And so what really happens is you take the qubit, do stuff to it, and then the qubit comes out after the stuff. And if I could write it, it'd be better. And there's also a bit that comes out from the stuff. So you can't have C2 coming in, C2 coming out, and 0, 1 coming out. And so if you undouble this, just this is a brief aside. If you undouble the thing on the top, you get something like this, with 2 legs coming in and 1 leg going out. And if you undouble the one on the bottom, you get something like this instead, where I have 2 legs going out. And maybe I should be a bit more disciplined about my legs. So 2 legs coming in, 2 legs going out. And then actually there is these 2 touch. Let me draw it with one. It's this. I don't know why I didn't just try to do this. It's like that. There are 5 legs. 2 double, and then a leg coming out. And this is, and if you just take, if you disregard the copy leg, there's also this map here, which is the decoherence. So where you do the measurement, but throw away the outcome. And this is just, you can open it up to be 2 spiders with a little bridge in between that does the partial trace. So it's 2 copies. And that is just the decoherence in the Z basis. Full decoherence, by the way. I mean, I know some people have like a continuum of partial decoherences. This is the actual, take the block sphere and squish it on the central axis. But of course, that's never a physical process that happens in one go. The decoherence process is typically as time goes by, you start from the sphere and you sort of slowly contract towards the central axis. You exponentially in the T1 time, and those are all partial decoherences, and this is just the end of the process. So that's when you're left only with everything has collapsed on the middle axis of the block sphere, and you've lost your phase. So anyway, just a point about the fact that there's various notions of measurements, and you can capture them by slightly different diagrams, which is also, you can write it like this. Good. So going back to my table. Now, what is the point of Mermin's argument? The point of Mermin's argument is that you don't actually take that probability distribution. You instead do some operation on that probability distribution. So you post-select it, right? I said in the morning, you take your outputs and you do a classical XOR. Sorry, you post-process it. I didn't want to say post-select. I apologize. So you apply some classical post-processing so that the table becomes something simpler. The table now only has one bit coming out of it. And it's become something like, if you do the XORs, it's either 0 or 1, take the XOR of all of these bits. I'm going to color this bit green. And it's 0, 1, 0, 1, 0, 1, sorry. Why did I 0 1 1 0 0 1 1 0? That's the XOR of the outputs. And now I can redo that table, and I can just keep the binary XOR by adding up all the relative all the probabilities of the various outcomes, and the table I get is deterministic. So it only has zeros and ones in it. And I get, something like this. So I only have two outcomes now, 0 or 1. And the probabilities are 1, 0, 0, 1, 0, 1, 0. And that's it. So I simplified my argument by post-processing my data, my classical data, and only keeping the information that I feel I need. And now Mermin's argument goes as follows. Imagine that our ignorance of the outcomes, so this randomness, or the determinism as well, doesn't matter. Imagine that it came from us not knowing something about the universe, something about the local processes, that the initial state, and there's some knowledge that we could possess that would tell us with certainty what the outcome is, 100%. And so really, we have to ask, first of all, it would tell us this outcome. It can't tell us the outcome always, because we have some inputs. So let's say it tells us the outcome based on the inputs that the parties have chosen. So the parties have chosen 3 bits, and based on 3 bits, there's some further knowledge about the universe that would tell us what the outcomes are with certainty. So if we knew something, if we knew everything, we'd be able to tell. This is very much it's been the guiding principle of classical physics for centuries. It's the thing that made classical physics successful. The idea that you never give up on trying to figure out how to better control the systems you have until you can effectively almost always predict stuff. Then you hit statistical mechanics and people say, you say it, but there's a limit to our maths, there's a limit to our brains, and then there's a limit to our computers. So we want to have, maybe we can't know the position of all the helium atoms because the demon knows, but we don't. So we have to somehow package it, but we have some aggregate quantities that we know for certain. And then quantum physics comes in, and the question is did something fundamentally change? And the answer, of course, is yes. And so we pretend that we have knowledge, certain knowledge, so that based on all the choices that the parties make, we can predict the outcomes. That's always possible, actually. You can always do that. But the issue is that our knowledge cannot make use of what the parties did globally, because these parties have been sent to faraway places. I mean, from the point of view of one party, if we obey the rules of covariance in relativity, the other parties might not even exist anymore. Like the universe could have ended for them. There could be a big black hole that has swallowed them. So we might want to assume that whatever knowledge we have, whatever dependency it has on the inputs of the parties, it obeys the rules of relativity. It is local to the parties. So we can start with some state that is shared. We know everything before the start of the experiment, but then the dependency on the outputs of the on the inputs of the parties is purely local. And this is what's known as a local hidden variable model. So it's a local hidden variable model. And it consists of saying that I know the bit that I know the outcome that Alice would get when she chose 0. I should call it something else. Let's call it X outcomes for Alice, Bob, and Charlie. So I know the outcome for Alice when she chose 0, the outcome for Alice when she chooses 1, the outcome for Bob when he chooses 0, the outcome for Bob when he chooses 1, the outcome for Charlie when he chooses 0, and the outcome for Charlie when he chooses 1. And these are all bits, and I know them with certainty. So I presume that if I have sufficient knowledge about the universe, then I can know this certainly. It doesn't matter if I make a probability distribution, because if I have a probability distribution, I can always say, I take my probability distribution, I take whatever event space is underlying my probability distribution, and I take that in addition, and I say that is further knowledge I can have, so I fix 1 point in the event space. So I can know about it. If there is a probability distribution, I can know what the event was, and I can fix that knowledge too. So I can freely imagine that if I can do this, then I can do it deterministically. Then I know that this can be done. So I take these outcomes. And I ask, is this compatible with what I observed? So let's see. When they all choose 0, the outcomes have to sort to 0. So I have an equation which says that the outcomes for Alice, Bob, and Charlie when they all chose 0, must XOR to 0. I know that when Alice chooses 0, but Bob and Charlie choose 1, then the outcomes XOR to 1. And I know similarly that when Alice chooses 1, Bob chooses 1, and Charlie chooses 0, they XOR to 1. And finally, that when Alice chooses 1, Bob chooses 0, and Charlie chooses 1, then this XOR to 1. And that seems innocuous enough, but it turns out that this system of binary equations cannot be satisfied. And the way to see, this is the standard trick in linear algebra. This is just linear algebra over the field Z2, but it's still linear algebra nonetheless. The standard trick is that I can take XOR of the individual equations and check whether I can satisfy the simpler equation that results effectively. So I XOR the columns of this system, and I get 1 on the right. And on the left, I notice that all of my terms come in pairs, so that it's this and this cancel out, this and this cancel out. So let me use a double like that. That x0b, x0b cancels out here, x1b cancels out here, that x0c cancels out here, and x1c cancels out here. So actually these are zeros. And so I have that 0 XOR 0 XOR 0 is not equal to 1. And that's absurd. So that proves that there is no way to be able to predict locally, just based on the local information provided by the party choice, plus any information from their past. There is no way to predict the outcomes that are witnessed by Mermin's experiment. And this is more generally, this is a very strong non-locality argument, because it's a non-locality argument that doesn't rely on probabilities. You post-select in such a way that it becomes deterministic, so you're only doing Boolean reasoning. And because it's only Boolean reasoning, what it says is that if there is a, and here we go way beyond the realm of diagrammatics and into other work on non-locality and contextuality and causality, what it says is really there is a polytope of possible correlations that you can obtain from these non-local arguments, the no signaling polytope. And what this says, the fact that it only has zeros and ones, what it says is that this particular model is on the face of the polytopes. It is maximally non-local in some sense. You cannot do any better than this. Well, you can qualitatively do better maybe, but quantitatively, this is as good as it gets. And so for two parties, you can't do it. So Bell's argument is in no way close to this. Bell's argument is not, it relies on the probabilities exceeding a certain correlation by very little, actually. While this argument doesn't even have a local fraction. So there is no amount of this argument that can be explained locally. While for Bell's argument, quite a good fraction of it can be explained locally. I don't remember how much, but I can look up the numbers. There's actually a very nice, I completely went beyond the realm of diagrams. I hope that you don't mind. And this is like, this is not diagrammatics, but it's still categorical. So still fits within the, hopefully the, the purview of this visit. So just to show you. No, wrong paper.
Can I ask
Shoot.
a question about what you just said?
Yeah.
So classically, there is a maximum you can get for the
Yeah.
maximum.
The maximum for.
Well, I'm counting, here for, it depends how you count, okay? But I'm counting.
For the game.
Yeah. I'm counting for classical. But the question is, from 2 to 4, there is a lot of space. So if instead of getting the GHC state, you get some other entangled state. I mean, can you make a similar argument in another state that is not GHC, but is entangled? But not necessarily maximum. An argument that there is no way classically you can explain?
There are plenty of them. There are plenty of variants of the GHZ state that work. There are plenty of qubit states that work, and the structure of why they work depends on the certain properties of abelian groups. So you can do this argument for qubits for arbitrary abelian groups. That was one of my early papers on this. And there's an entire, I don't remember the conditions, but I can go look them up if you give me 1 second. Is it Mermin, generalized Mermin type non-locality arguments with Will Zhang. So in this paper, which is fully diagrammatic, actually it's mostly diagrammatic, this is ZX calculus for qubits. So it is very much what we've been discussing all of these days. What we did was we looked at this kind of generalized arguments where you have effectively you start with a GHZ-like state, but for qubits, but you could have phases on it, and you measure in the strongly complementary basis. So you measure in the Fourier basis, or you start with the GHZ in the Fourier basis and you measure in the computational basis. It doesn't really matter. And you're allowed to perform certain phases. So you're allowed to perform some rotations in the same basis as the GHZ state. So the same as Mermin's argument, but for arbitrary qubits and arbitrary finite abelian groups. And then you ask for which of these groups and for which choices of phases do you get non-locality? And is it always as strong as Mermin's? And the answer is there's a condition on the groups that you can impose. And if you give me a second, I'll find what the condition is. Yes, it is contextual in a system. Yeah, so there's a system of equations that you can write in the abelian group. So you can do Z module arithmetic. So not in the case of Mermin, you're working in the field Z2. In the case of general abelian groups, you have to treat them as Z modules. So you're no longer working with vector spaces, but almost. And you have to take care of the torsion, but it's fine. And you can still do Gaussian elimination. So you're still trying to solve a system of equations in something sensible. And this system of equations in a ring has solutions if and only if the model is contextual. And when the model is contextual, then it is maximally so. And when the system has solutions, then the model is not contextual at all. So these GHZ-like states, even with certain classical phases, they're one or the other. Either it is fully explainable or it is maximally non-local. And they generalize to arbitrary categories, by the way. They're not just in quantum theory. If you pick a different fields underlying the theory, pick the reals, you pick some cyclotomic field, you pick the p-adic numbers. There are conditions in the field that tell you when this has solutions, and if it does, then it's kind of independent of the field. So it says it's one of the nice results that if the system admits solutions in the group, and you can formulate the argument in the field, then it is always contextual, as long as the field is positive, as sort of as a positive semi-ring of scalars. Yes, with phases, classical phases, but phases, yes. So for qubits, you have lots of phases that you can add, and you can make the argument for arbitrary GHZ states.
Compatible, I mean, whenever you are violating maximally, maximally, no, contextually.
Yeah.
Maximally contextually. Is that the case where if you calculate the purity of the state over the direct sum of SUV, it's 0?
Which state? The state.
The generalized state that.
The GHZ state.
The GHZ generalized state that maximally is contextual, is equivalent of the GHZ.
Yeah, they're all pure.
They're pure.
Pure, yes.
But I want to calculate the purity. The purity is a quantity that gives you a measure of entanglement. Those maximal entanglement with respect to SUV plus SUV plus SUV.
Yeah, I think so. I think so.
I would like to see.
Because they're all actually, I'm pretty sure that we can do that now. So is it just the purity of all the possible marginals? Is that what the calculation is?
Suppose you have a bell state.
Yeah.
Just for qubit.
Yeah.
Okay, so you have a bell state 0, 0 plus 1, 1, for example, or any bell state.
Yeah, any. Okay, let me write it.
You have to calculate 1 over 2 waka. So write this formula. Waka.
Yeah, hang on. Yes. Yeah, 1/2.
Waka the sum over, I would say, mu. Well, mu equals to XYZ. And another sum over I equals to 1, 2. Of the matrix element, you have psi, something in the middle of psi.
So the matrix.
Psi, it's a bra.
It's a bra. Yeah. Okay.
Prop psi.
Prop psi.
Now you put sigma mu I. Sigma mu means sigma x or whatever.
Yeah. Yeah. I got it. Yeah.
I is 1 or 2.
Yeah.
Psi.
Yeah.
Squared. No, well, yeah, it's not necessary, but okay. For this case, it's not necessary. So that quantity there is bounded by
without or with, like that's the
you can put it in this case, put the square directly. It doesn't matter.
It doesn't matter, right?
It doesn't matter. No.
Okay.
Because the admission doesn't matter.
Yeah.
So,
okay.
So you have to put the square. No, you have to put the square.
Do I?
But the square as a modulus or not modulus doesn't matter.
Oh, okay. So this, sure. Yeah. Okay, I get it. So you still want it squared.
Yeah.
Okay.
That quantity is bounded, if psi is normalized, it's bounded between 0 and 1. If you put psi equals to Bell state, is 0. It's identically 0.
Yes, it is.
Put it.
Well, they're all 0.
Sorry?
They're all 0.
Yes, that's what I'm saying.
All the terms are 0. Yes. Oh, yeah, correct. You're square.
Yeah. It's 0.
Yes, it's 0.
But if you put the product state, this is 1. You put 0, 0 or 1, 1 or whatever, 0, 1, whatever that quantity gives you 1.
Does it?
Yes. But okay. Now my question is.
Really?
Yeah. This is the purity.
Oh, pure state. Yes, it's true. Yeah, because it's the sum of the components of the state in the block ball. Yeah.
But this idea generalizes. This case is trivial, but generalizes to any other. So that quantity is the purity with respect to SU2 plus direct sum SU2, because there are 2 speeds. And 2 cubed.
Why plus, not times?
Because it's the algebra.
Oh, fine. Yes. Okay. Yeah. Okay. Yeah. Got it.
So now I'm asking you the question. In your case, you have a qubit. Okay.
Yeah.
You have, I don't know, 3 parties or 4 parties or whatever parties. Now, in the case of Mermin,
yeah.
If I do this for Mermin,
yeah.
Mermin is 3 spin 1/2.
It's still 0.
Still 0.
Yeah.
So when you have to use there, but you have 3. So you have to sum over 3. You have to do, I think, 1. I think it's 1 over 3.
Sure. Doesn't matter because it's 0 non-zero, but yeah.
Yeah.
Sure.
And it's going to work. And if I give you anything, the only thing I need to change is the algebra. What I need to change, I mean, these are qubits, it's always SU2, so you have sigma x, sigma y, sigma z. But if you have, for example, some object that has 3, dimension 3 instead of dimension 2, it says SU3. And so on and so forth.
Hang on. But the sum of squares for a pure state is not going to be 1.
For product state? No, it's
for qubits, it's not 1. For qubits, it's not 1.
No. It's 1. You have to put the normalization. It's bounded. You can make it bounded from 0 to 1 by adjusting the normalization, the 1/3 or the 1/2.
Yeah. And my point is that for pure qubit product states, the sum of the squares of these coordinates is always 1. It is true for all of them uniformly. For qubit states that are not qubits, the sum of the
you cannot put that qubits, you have to put there
a different algebra. Yeah, sure. The one for the, let's say the one for the algebra derived from the poly group.
Well, I don't know if you can put it, and it says U3. For example, you have 3 levels.
Yeah.
The spin 1, it says U3.
Sure, but and you have to take the.
U3 has 8 generators.
Yes, okay. Which you can write down fairly easily.
Yeah, I know.
You can pick any 8, but what I'm saying is that the sum of the squares no longer sums to exactly 1 for pure states.
If you put the adjust, you have to adjust 1/3. This is the factor in front. Okay, it's important. That factor 1/3 You have to change depending on the group.
But
Yeah, I don't.
okay, so hang on. In the case of qubits, it is true that this is 1 with the correct normalization factor. It's 1 if and only if the state is a pure.
All these states are pure.
If and only it's if and only if in the case of qubits.
Yes, but it's true in general.
No.
Yes.
No. No. That the sum of the squares is 1 if and only if the state is pure is not true.
I say, depending on the dimensionality of your Hilbert space,
Yeah.
you have to adjust the algebra.
Yeah. And if you adjust the algebra.
If you adjust the algebra and the factor that is in front,
yeah,
it's always true
that
any product state
is true. So even for what? Okay, let's take one system. Okay, only one. So let's take the simple case where we have this, just this.
Oh, but there is no entanglement in this case.
So
it's only one.
Okay.
No,
okay, take a product. Sure.
You can define.
Okay, take two and get one product state. Take a product state.
Yes.
Yeah.
That thing is bounded. It's a number that is bounded between 0 and some number.
Sure.
The upper number, is always a product state. And you put 1 over that upper number.
Sure.
In the front thing. So
yeah.
You normalize everything to 1.
And so you're saying that this equation defines product states in general.
Yes.
In general.
Yes.
No.
Yes.
No.
Yes.
No, because they would be spheres.
What?
They would be spheres. That would make that the pure space of states is a sphere. But that's
they are always how do you call extremal states.
Sure, but
they're all extremal. I mean, you can formulate this. I can give you all the papers. I mean, we wrote these papers in 2000. Okay, so
I think I'm saying something slightly different from you because, and here's where I'm coming from, and maybe this is I'm sure it's a mismatch in what we're saying. The equation for a product state in this case, what you're doing is you're summing over the coordinates of that state in the algebra of observables, taking away the I component, which is the normalization component.
Yeah.
And if you have a product state, you're doing it for one state on the right and for one state on the left, and they're independent because in the product state, one always has I and the other one always has something. So if I is equal to 1, if I have a product state and I is equal to 1, then the non-trivial generators for the Lie algebra, so the non-identity generators, which are in your case, the generators of the Lie algebra without the global phase, are only on the left state, and the right state is just 1. It's traced against itself. In that inner product, if you have sigma mu I, it means it's sigma mu 1, and on the right you just have it's a product state, right? So on the right the state cancels itself out, and so you get the sum. This is the sum of the squares of the components of the two states in the product with respect to the generators to the non-identity generators of the Hamiltonians or of SU and so it's the same. They have the same. SUN has but you're taking these to be Hermitian, right? Your generators.
Well,
maybe not.
Generators are Hermitian.
Correct. So I'm going to say the generators of the space of Hamiltonians, which is.
Well, I mean, but it's SUB. I mean,
but it's the same. Yeah, of SUD, of course, 100%. Okay, and now I'm saying that quantity is the fact that quantity is, well, I don't know, 2 or 1 if you normalize it correctly, seems to be somehow related to the fact that the 2 points lie on the surface of a hypersphere.
They are extremal points.
But that would mean that the geometry of the pure states in a qubit is a hypersphere.
So it means that you have to define convex cone.
Yes.
That convex cone will have extremal states.
Yes.
And those are the pure states. Those are the pure states that are product states.
Of course.
These are the extremal points of the convex.
Of course. And in that convex cone, these product states somehow, because you're taking the square of the coordinates, the sum of the squares of the coordinates, and you're setting it to 1. Yeah, of course. Yeah, it's fine. It's the radius of it. You're saying that they lie on a sphere.
Yes.
But that I'm not necessarily concerned about. What I'm saying is are you saying that that exactly the product states for arbitrary dimensions always lie on a hypersphere?
Yes, they lie on the extremal points of the convex cone. I'm sure it's a hypersphere.
Well, if the sum of squares of the coordinates is equal to 1, no, even in the general case, it's going to be a sphere. So it's a hypersphere, of course, not a sphere. That is it. But and they are all exactly the ones that give 1. Exactly.
Yes.
No other ones give 1.
Yes, absolutely.
That is extremely fascinating. So the product states form a.
No, but what I want to know if the states that you are saying that satisfy this, maximal
they do.
extra thing.
Yeah, they do.
Exactly the ones that give 0 from the analysis of this point of view.
They are not exactly the ones that give 0, no.
Well, I mean, the case of the GHC gives 0.
But the GHC is not exactly the one that gives 0, right? There are many states that give 0 for 3 qubits. They are not all GHC states.
In this case,
they're all GHC states.
Maximal entangled gives 0.
Yeah.
Only maximal entangled gives 0.
Not all maximal entangled states are GHC states.
No, they are in the middle. You can get 0.35, you can get anything because this number can oscillate between 0 and 1. Okay, once you normalize properly. And all states, I can give you a whole list, even tables of all the states that are in the middle.
Interesting.
And what I wonder is if the states that you are saying that from your point of view, maximal contextuality are the ones that give 0 from this point of view.
They're not exactly the ones that give 0.
Because I can see that, because I could argue that.
Well, maybe they are.
All the zeros satisfy that.
They all give 0. All the GHC states give 0.
No, GHC gives 0. All the GHC generalized.
Even the generalized ones, they always give 0.
Yeah.
So that's okay. So that's good because actually the only thing that happens is that they are Bell states. Once the GHC states.
Generalized Bell state.
No, but in this calculation, because you're only looking at 1 qubit at a time, the GHC states have. However many legs they have, however many dimensions they have, what you're doing is putting a matrix in one of these legs, and then the other ones are getting contracted. So by fusion, they're actually the same as the Bell state. So they give 0 because the Bell state gives 0. Yeah. So they in that sense, it is okay. I think like this. Yeah. So the calculation is the same as the Bell state. The generalized GHC states don't all. I mean, probably the ones that satisfies these arguments do give 0 as well. Definitely the ones that, but the phases that are in the middle, you're saying the state before I measure it, after I apply the phases, should give 0. That.
I mean, the ones that give exact 0 are the ones purity 0. We call this purity with respect to analysis. And the other we are thinking about measurement.
Yes.
It depends what instrument you're using.
Yes.
But that algebra, I mean, in the cases that you're analyzing, I would argue that all the maximas are at least 0. But my question is if there is something that is not 0, that it still gives you maximal contextuality. That is the question.
So I'm looking. That's why I'm looking at these phases that arise, because it is probably possible, but I'd have to look at it because
I mean, I don't want to capitalize everything here. I mean, because people.
Oh, you're asking.
But this is an interesting question. I can show you. Show you some works. I mean, we did this work with Mannequin. I mean, like 20 years ago.
Can you send it to me?
I can send it to you. Yeah.
I'm still kind of flabbergasted by the.
I know, but my question is not about that because this ain't gonna work.
No, but sorry. Just to explain, the reason why I'm so flabbergasted is that I know of a lot of works about the geometry of higher equivalents of the block sphere, of the block ball, and it's not a sphere for any dimension other than 2. So 2 is the only dimension for which it is a sphere.
Yeah, it could well be, I was going to say, that's the reason why I say I'm not sure it's a sphere, but it's a convex cone for sure.
No, but the points that have sum of the square coordinates equal to 1 are a hypersphere. They are, because that's the definition of a hypersphere. So that's why I'm confused. That's why I find it's, but you're saying these are the product states. So it is very much, it is going to be the case, I'm sure, that if I look into it a bit more carefully, the whole space of states is not a hypersphere, but not even the whole space of pure states is a hypersphere.
Which are indeed the product states.
Extremal in the sense of this metric.
Yes.
Okay. Because in the spaces, the extremal ones are just the ones on the boundary, and that is not enough to even give purity in higher dimensions. So you're saying that the extremal ones with respect to the, of course, the extremal ones with respect to this metric are exactly the pure product states. And so this would say that the hypersphere defined by these equations, so by the extremality in this equation, characterizes exactly the product states in arbitrary dimensions for arbitrary algebras. That is beautiful. No, but that is beautiful. It's beautiful. I mean, I had never really understood that. That is very nice.
But I'm asking now the other question.
Yeah.
The question about measurements of, and the reason is you will know where I'm getting. Because now what I want to do is something else because of an experiment. That is, Roger asked the other day, we have this instrument that is functioning pi/2 mode, and we have now the equivalent of a neutron that is in 4 states in one path and 2 states. You know, it's in one subsystem and 2 states in the other. You know, it's like there are 4 energies and 2 spins.
Okay.
And what kind of measurement we can do to show that there is a violation of some contextuality type of inequality. That's the reason why I'm asking the question, not because of this. Yeah.
So what's the state? What's the state?
Oh, the state is something.
First of all, what's the system? Sorry, how many degrees of
speed times 4 level. So 2 speed and 4 another.
So it's an 8-dimensional. It's an 8-dimensional. So I can do it as a 4 C4 times C2.
Yes.
Something like that. Okay, so something like this.
Yes, exactly. Yeah.
And what is the symmetry in spin, I presume, is Z2?
Z2.
And the symmetry, no, but I mean, yeah, you have plus minus spin. So the abelian group that would be relevant is Z2. What about the C4 part? Is it like a cyclic thing? Is it
yeah, well, the problem is that they don't know exactly what the state is experimentally. Okay. That is part of the story. I mean, they presume that it's an equal superposition of these different states.
Okay.
They don't know.
Okay.
That's the reason why they want us to write down a contextuality inequality to see what is the state.
Okay. And you have only one of these.
Well, the thing is that, you know, this is something called Nietzsche. Nietzsche technique. This is used heavily in neutron scattering in all facilities all over the world, okay? And the thing is, some instrument that they claim that if they put some flipper, some they call pi/2 flipper, that they get something like nothing works here.
Yeah. By the way, presume that I know nothing about this because
no, it's okay. I mean, that's not the point. The point is that they are, you know, they have, like, let's call, they claim, this is the claim, that there are, like, you know, 4 energies. They can generate, the neutron may go into 4 possible energies.
Yeah.
And they can adjust this.
Yeah.
Okay. And it has, because it's a fermion, you know, it's a neutral fermion with a spin 1/2. Yeah. It can be this. Yeah. Okay. So then the state space is essentially
C4
you know,
cross C2.
We have exact, well, yeah. I mean, so for example, this is one possible state. It could be that you get this E, let's say tensor up plus, I mean, they don't know exactly what the state is.
Yeah, okay.
I mean,
but they don't know, in principle, they don't know that there's any specific super selection rule that limits the kind of states.
No,
it could be anything in that.
No, absolutely. Oh, no. So the whole point is, if we can derive some sort of inequality, because we have done that for other configurations, okay, and we've been successful. I mean, I don't know, unless experimentally have cheated, I mean, which could be, okay, we don't know, but we're successful. But if we can design some sort of contextuality inequality for this situation, such that we can argue that the state that they generate is maximally entangled in.
What are you?
I'm just going to broadcast you guys.
Yeah.
But they
So
don't
we are talking
understand.
about experiments.
They don't understand what's going on.
Amer, are you there or you left?
I am here. Yes.
I don't have audio on this one.
I am also here, and I am interested in what's going on.
Okay,
have
so
some
shall we point the
familiarity with
camera
the
at
experiment.
the? Yeah.
If you want, you can do it over.
Do you want me to point this camera at the
or
board?
you do the desktop. What are we on? I mean,
Because I think the desktop doesn't. I don't know if we can zoom into.
I see.
to
I
see
can
that's
come
the-
next to you guys.
Okay.
Now we have a cameraman.
Yeah, okay.
So I'm stopping share screen. Okay.
There are some instruments, so
Yeah.
let me say, there are some instruments that come in different flavors. One is called magnetic Wollaston prism.
Yeah.
Okay, this is like the polarizing beam splitter for things.
Perfect,
Okay.
yeah.
Now these are some instruments that they built here indeed at IU. Okay, that for example, there are different configurations of these instruments, and these instruments are like an entangler. Think about this about an entangler. Okay. So this is an entangler. You have a neutron beam that is coming from here.
Yeah.
And now the claim is that here you have a state that is like a state where you have, for example, here in path, you can say that this is path 1, path 2. By the way, all these things have been measured. So this is path 2.
Yeah.
And here you may think that your state here, it's an assumption in principle, is like path 1, let's say spin up.
Yeah. Plus path 2 spin down.
Plus path 2
So-
spin down over square root of 2.
Okay.
I mean, that's a claim. Is it true? Is it true? That is a question. Is it true that this is what they're doing? Okay, we design experiments where we prove it's true.
Okay.
Okay. By changing this, by doing many things. So we prove that this is true.
Okay.
And the way we did it is we constructed experimentally. Of course, you have just all these things. We constructed a witness that is like a CHSA witness.
Oh, I see.
And in that way, we prove that the state was this because we got the 2 square root of 2. Okay.
I see. So you want to get into a situation where you can not really look at the degree of freedom, but get a number that.
Exactly. And there is a many good reason for that because we want to use this as a new way of imaging materials. Okay. So, but in principle, we know this. Then we know that if we do RF flippers, we also know that.
Okay.
And we can use a different kind of instrument that adds, for example, energy, path, spin, and energy.
Okay.
Now we can construct a GHC state.
Okay.
And then we design an experiment that shows 3.
Yeah.
So we show that indeed we get 4.
Okay.
So we consider we got 4. So Mermin's equality.
Yeah.
So it works.
Yes.
Okay. And what works? I mean, of course it works. The point is if experimentally it works. Okay. Not that the equality works. So that works. Now there is another instrument that is this MITSE.
Yeah.
This MITSE instrument is very interesting because it can measure time correlation.
Okay.
Okay. But the point is that it's different. It functions differently. For example, there is no path.
Okay.
It's only one path.
Yeah.
Okay. But you can entangle in energy and spin.
Okay.
But the problem is that there is one configuration that is called the pi-pi configuration for the instrument where we can get something that is like a best state.
Okay.
So we get
So
something
that
like
is-
this.
Okay. That's
And
okay.
that experiment is going to be done soon.
Okay.
Okay.
But what can you measure?
What you measure is the polarization. And then you
only
backtrack.
measure this degree of freedom.
You measure this degree of freedom.
And nothing else.
And nothing
Oh,
else.
that's
But you have the final state.
And what can you do?
And
On
that
this,
is-
what operations do you have?
That's what I'm going to say.
Excellent.
So you measure the polarization, for example, along X. Okay.
Mhm.
And what you do is you rewrite this now as something that is the state that you believe here. Let's call this B.
Yeah.
The state that you believe was here times some unitary, let's say sigma X times some unitary.
Yeah.
Okay.
But that's for that case up there, not for this.
Yeah.
Okay.
So we did this, and indeed these things, then you write as a witness.
Yes, of course.
Okay, then you write this as a witness, and then you get the matrix element for each angle. You get a matrix element of the delta state. Then you construct a CHSH in that way. With Mermin, we did the same thing. But what I'm saying is now in this configuration,
what can you do there? What are the operations what are the unitaries that you're allowed to do on that system?
we don't know yet.
Oh.
The only question is, we have, because there is further question about constructing the witness. Okay, so you need to construct the witness. Once you construct the witness now for an inhomogeneous system, now you don't have two things which are equal, because I have four energies and two of these.
Yeah,
so
it's kind of irrelevant though. It's an eight-dimensional system. So
right, but I want to construct a witness that is essentially doing that. The next step is to look at the unitaries. And then
how can you construct a witness? I mean, what you say, the thing is, you're saying construct a witness and you know what you can do. But to me, this is
I don't know how to construct the witness.
No, but to me that's a wire, that's a completely black box thing. I have no idea what is legitimate and what isn't legitimate. So what you can only measure this degree of freedom.
I can always measure this degree of freedom
and nothing else.
And nothing else. And I need to construct a witness in this way.
But you cannot do any rotations, any transformations, any.
No, there are transformations you can perform, but the transformations will be adapted after I know what the witness is. So after I know that this was a CHSH witness, I knew what I need to do to the system, okay, in order to do the right rotations to put to construct the witness.
So you're saying once you tell me what I should measure, I can construct the circuit. So
because I can go to the instrument and say, okay, I want to put, a coil that is going to change the spin by a certain angle.
So I am free to write down a circuit for this.
Yeah, you're free. Okay. But you're free at a certain point.
Okay.
The experimentalists, they have some
real life constraints. Storm will be here in say 10, 15 minutes.
Okay, we can go here tomorrow.
Which storm?
A new storm.
A new storm.
Yeah. New storm. It's
tornado
like
storm.
Gigantic storm.
Oh, so we have to go home.
It's like
yeah,
it's like a really bad one that is actually
okay.
Storm is coming, so we have to say goodbye.
Bye.
See you tomorrow.
See you tomorrow.
I don't want.
Thanks. See you.
Thank you.